Okay, so hello everyone. Welcome to the problem solving session for Discrete Maths, week 2. So last time what we did is we looked at some examples of counting. We saw permutations and combinations and rule of sum, etc. And we also saw a technique called stars and bars counting, and we did some examples on the same. So there was a question that we could not cover last time because of lack of time. So what we will do is we will start with that question, then we will cover the topics for this week. So we will look into set theory, we'll understand what are sets, and we will see some basic operations on the sets. And finally, we will also understand some laws that are very useful. And we will do this, we will define the concepts quickly and we will look at the examples. Okay, so that is briefly what we are going to cover this week. Okay. Okay, so let's begin with the question from last time. So I'll read out the question for you. So the idea is, so this is something you'll be able to do using the basic ideas of counting. So you do not need set theory, etc. for that. So I'll read out the question. So you have 8 distinct pieces of food, and what you want to do is you want to choose 3 of them for breakfast, 2 of them for lunch, and 3 of them for dinner. So the question is, in how many ways can you do that? So I'll let you think about it for a couple of minutes, and then you can let me know. Yeah, we can discuss the ideas. I'll just write down the question here, and you can, meanwhile, you can keep thinking. Okay, I see one answer in the chat. So 45 is one answer. Okay, we will discuss that. So what is your idea behind this? Could you maybe tell us the intuition? Okay, so I see one answer in the chat. Anybody else or people who have answered in the chat, would you like to explain the idea?
Ma'am, I think it is a example of stars and bars, and there are 3 categories in which we can put 2 bars. So by applying formula, we can elaborate its answer.
Okay, so I see. So we will discuss this in some time. So yeah, anybody else, if you have any other ideas or any other answers, I'll wait for some time and then we will look at the solution. Okay, so let's let's look at the answer. Okay. Okay, so what I'll do is I'll first describe one method of doing it, and then we'll come back to the stars and bars approach. We will comment on that. Okay. Okay, so you have the question says that you have 8 different varieties of food, and what you want to do is you want to choose 3 of them for breakfast, 2 for lunch, and 3 for dinner. Okay. Okay, just give me a second. Okay, so the question is, in how many ways can you choose your items given that you have eight varieties of food? So that is naturally 8 factorial. Okay, so now the question is that you want to choose three items for breakfast. So let's say one item that you have is idli, the other item is say aloo paratha, and the third one is, let's say, poha. So the question is, if I write this, if I rearrange them, so let's say I write aloo paratha first, and then idli, and then poha, then should the two sets be should we consider these as different different arrangements, or should this essentially be the same? Because all we're asking is we want 3 items for breakfast. We don't care what the order is. So when we write 8 factorial, we are essentially overcounting the number of breakfast items by a factor of 3 factorial. So what I should do is I should divide this whole answer by 3 factorial, since I'm overcounting the breakfast by 3 factorial. Is this okay? Okay, good. So yeah, if that is fine, can someone maybe tell me, let's say for lunch, since there are 2 items that you want to choose for lunch, so how much are we overcounting it by? Okay, 2 that's right. So I'll divide it by 2 factorial because of lunch. Okay. So again, now the third question is, what about dinner? So how many times are we overcounting for dinner? Okay, so is it 3 or is it 3 factorial? Okay. So yeah, exactly. So the point is that there are 3 factorial many arrangements you can make with 3 items, and hence you should divide by 3 factorial. So what we did is we looked at all possible ways of arranging the food items, and then we divided by the number of overcounting. So let's calculate what this value turns out to be. You could also try this in parallel. Okay. So this is 8 into 7 into 5 into 2, which turns out to be 560. So this is what you're getting. Okay. So is this fine with everyone? If there are any, okay, good. Okay. So what we will do is, this was one method of solving the problem. What we will do is we will look at another method by which we can solve the same. So maybe I'll call this solution 1, and now we will look at a different way of solving the problem, and then we will go back to the stars and bars counting. So let's look at solution 2. So yeah, so as the question says, you have 8 varieties of food, and these are all the distinct items. And now let's say I want to choose 3 breakfast items out of these 8 varieties. So my question to you is, in how many ways can you choose 3 breakfast items from 8 varieties? Okay, yeah, I see an answer that is 8 choose 3, which is correct. So you have 8 items and you want to choose 3 of them, and the order does not matter. So the answer is 8 choose 3, which is fine. Okay, so yeah. So the next question I want to ask you is, in how many ways can you choose 2 lunch items? So say you had 8 items here, out of these 3 are already taken into breakfast. So how many items are remaining? You have 5 items, and now you want to choose 2 lunch items out of these 5 items. So the question I'm asking is, in how many ways can you choose 2 lunch items out of 8 minus 3, which is 5 items? Okay. So I see an answer, which is 5 choose 2, which is correct. So the idea is same, that the order does not matter, hence you use the combinations. And now you are left with, so you had 3 items, 8 items, 3 of them were for breakfast, 2 of them you chose for lunch, and now you're left with 3 items and you want to use them for dinner. So the question that I'm asking now is, in how many ways can you choose 3 dinner items out of the remaining 8 minus 3 minus 2, which is 3 items. So what do you think? Okay, good. So the answer is correct. So this is precisely 3 choose 3. So now you have solved, you have asked 3 questions and you have answers for all of them. And now what I'm asking you is, how do you combine them together? So ultimately you want to find total number of ways in which you can choose 3 breakfast, 2 lunch and 3 dinner items. The question is, how do I combine these answers? Do I multiply them? Do I add them? Or what do we do? Okay. So, okay, good. So the answer is, you are going to multiply them because, all of these events are essentially happening independently. The choices for breakfast were independent of the choices for lunch and so on. So what we will do is, we'll use this rule of multiplication, and this gives us that the number of ways you can do this is 8 choose 3 times 5 choose 2 times 3 choose 3, and this is nothing but, so I'll expand this. This is 8 factorial divided by 3 factorial divided by 5 factorial, and this is 5 factorial divided by 2 factorial, 3 factorial, and this is nothing but 1. So we will cancel off some terms, and what you get is 8 factorial divided by 3 factorial times 2 factorial times 3 factorial. Okay, and this is exactly same as the answer that you calculated in the first approach. So this answer here is same as the answer that we had in the first. So since you are counting the same thing but with different approaches, you should essentially get the same count. So is this okay with everyone? So we saw 2 methods of counting the same item, and we ended up with the same solution. So is there any question about any of them? Okay, good. So if that is fine, then what we will do is, we will look at the approach that Ojas was pointing out. So we will try to solve this using the stars and bars approach. Okay. Okay, so what you're saying is that you have some eight stars because the food varieties that you have are essentially the stars, and you want to partition them into breakfast, lunch, and dinner. So that means you want to put two bars so that you get three partitions for the breakfast, lunch, and dinner. So okay, okay, you need three partitions, and for that you need two bars. And now your n is 8, k is 3, and what you're basically doing is you're plugging it into the standard formula for stars and bars counting, which is n choose minus 1, n plus k minus 1 choose k minus 1. And if you just plug and place the values, what happens is you get 8 plus 3 minus 1 choose 3 minus 1, which is 10 choose 2, and this is nothing but 10 into 9 divided by 2, which is 45. And this is exactly the answer that was there in the chat. So now let me call this OGSS approach. So now the problem that has happened here is that you solved this problem using three approaches, and for the first two approaches you got the same answer, which was 540, but now this time you ended up getting an answer which does not match with the previous two answers. So can anybody see where the problem is, or do you have any ideas about what could have gone wrong with this? Okay, so anybody, any thoughts? Okay. Okay, so yeah, so is this the question fine? Is the question understood, or shall I repeat the question? Okay. Okay, so basically you have 8 varieties of food, and you're looking at this as 8 stars, and because you want to partition them as breakfast, lunch, and dinner, this is same as putting 2 bars. Okay, so then you just applied your standard formula for stars and bars counting, and you ended up getting with an answer which is 45. And the problem that happened here is that this does not match with the previous answers. Okay, so yeah, let me show you. So we tried this with the first approach, and the answer you got was 8 factorial over 3 factorial, 3 factorial times 2 factorial, and both the approaches matched. But here you're getting the answer you're getting is 45, which clearly does not match the previous two. So the question we are asking is, what could be wrong with the approach? Okay, so let's look at what what has happened here. So Okay. Okay, so let's see what went wrong. So um, the one, there are two problems with this. One problem is that what we said is that when you get these three partitions, whatever is to the left will be your breakfast items. The middle one would be your lunch items, and the ones towards the right, that the remaining ones would be your dinner items. But the partition we are making could be of arbitrary size. So for example, it could just give you one item for breakfast, three items for lunch, and the remaining four for dinner. So this is not what we wanted, because we have some strict constraints that you want exactly three items for breakfast, two for lunch, and three for dinner. So one problem with the stars and bars approach here is that it could make partitions of arbitrary sizes, and it may not match our constraints. So yeah, in particular, you have this example which does not match with our requirements. So that is one problem with the stars and bars approach. And the other problem is that it does not take into account that your breakfast could be any of the eight items, because you are, say, forcibly restricting your breakfast items to be from the left. And so let's say the first item is idli, then you have dosa, then you have let's say a roti, and so on. Then what happens is you did not allow yourself all the options, the choice of all the eight options for breakfast, and the choice of the remaining items for lunch. That is happening because of the bars, the positioning of the bars that we are restricting. Okay, so this partition is what is causing the problem. So that is just to summarize the two problems that we had. And yeah, so is this making sense? Okay. Okay, so just to summarize, what happened is the two problems that we had was that yeah, one is that you do not have the choice, and the other is that the partition size does not match. So that's the reason why the number of the number of items that you ended up counting were much lesser than the actual answer. So in this case, you ended up getting 45, whereas the actual answer was 540. Okay, so is this making sense? Okay, so yeah, so good. It was a good attempt, and in fact, it was a natural idea to think of the stars and bars here. But I hope everybody is clear about the problem that has that is there with the approach. So yeah, Kaustubh, I see a hand raised. Do you have any question? Okay, so if there are no questions, then we will move on to the next question, which is about sets. So what we will do is we will quickly recap some topics about sets that were covered. So let's go over it quickly. So let's understand what, and then we will go towards the problem. So let's understand what are sets. So sets is nothing but a collection of objects. Okay, so for example, I'll write a couple of examples. So for example, 1, 2, 3, 4, this is a set, or the set of people that are currently attending the tutorial. So Kaustubh, Isha, Shomrita, Ojas. They also form a set, and this is also a valid set. And the kind of sets that we have written here are peculiar in the sense that I have listed all the objects explicitly. So this is this is what is called a list or rooster form. And there is another method of writing a set, which is what is called which is what is called set builder form. So the point with the list or rooster form is that you just explicitly write down all the elements that are there, and you write those into curly brackets and separate them with commas. So that is your list, that is the list form for you. And the other notation that you have is what is called a set builder notation. So how do we write this? So we write this as set of all x such that x is say x is a natural number. So notice that in this case, in the previous two examples, it was easy to write explicit numbers, but if I go on writing this in the list or rooster form, then I cannot go on enumerating all the infinitely many numbers, because I simply do not have that much space. So something like this is not possible to write in the list format, and what set builder gives you is a succinct way of writing the same set. So here, if you just write set x such that x is a natural number, then you have captured the entire set without having to enumerate all of them. Another natural term that comes up with set is what is called cardinality, or the size of the set. So how do we define this? This is simply the number of elements in the set. So for example, if I ask you about the first set, let me call this S1. What is the cardinality of set S1? 4, right? So the cardinality of S1 is 4. And we denote this by 2 vertical lines between the set, and that's the notation. So let's say this is the set S2, which is consists of Kaustubisha, Ojas, Amrita, and the size of this is 4. So so anybody, what would the size of the So I'll just define one more notation called belongs to, which is denoted by the symbol epsilon. So this is says that, say you write x in belongs to set S if x is contained in the set. So for example, in the set S1, is 4 contained in S1? Yes. So good. So the answer is yes. So this will take a Boolean value of true. And let me ask, is 5 contained in the set S1? No. So 5 is not in the set. So this expression will take a value of false. And how do we write this? We write this with a slanted line. So what this means is that 5 does not belong to the set S1. So these were the two simple notations that I wanted to introduce, and I think with that in mind, we can now solve this problem. So I'll just read out the question. So you have a set of odd positive numbers, which are integers, which are less than 10. And what you're asked is you want to find the cardinality of this. Okay, I see some answers in the chat. So my first question, even before we find the cardinality, my question is, how do we write this set? So whether it's a set builder form or it's a list method, how do you write this set?
Ma'am, so in listing form, we can we can write this set as in curly bracket 1, 3, 5, 7, 9.
Okay, yeah, that is correct. So what we have is a rooster form of the set. We have explicitly written the elements of the set. So how do we write this in the set builder form? Anybody?
Ma'am, we can write this in set builder form as in curly bracket x bar. X is an odd number between 0 to 10.
Okay, so yeah, x is a odd positive number. Okay, maybe I'll just write it the way you said. So x is an odd number and x is between 0 and 10. Okay, so that is correct. That is indeed a valid representation in the set builder form. So now I'll ask you the same question. What is the cardinality of this set? So essentially, there are 5 elements in the set S, as you can see in the rooster form. So the answer is 5, which I think all of you have answered correctly. Okay, so we will move on to the next question. So okay, so the question is that you have a set S which consists of all numbers that are less than 100, and those are squares of some non-negative integer. And what you want to do is you want to tell what the set is. So okay, so I'll wait for some time, and you can others can also attempt it, then we will discuss the answers. Okay. Okay, so yeah, I see a couple of answers. So let's try to solve this now. Okay. So S is let me just write the set as S is a set of all numbers as x's which are squares of non-negative integers, as well as they are less than 100. Okay, so let's enumerate this one by one. So let's look at 0 square. So 0 square is 0, so 0 must belong to the set S. Then 1 square is 1, so 1 must belong to the set S. Then you have 2 square is 4, so 4 must belong to the set S, and you keep on going. Now let's say you are at 8, 8 square is 64, it is less than 100, so 64 is in the set. Then 9 square is 81, so 81 should be in the set S. And now you go to 10, 10 square is 100. But should 100 be in the set S? No, because we have this additional restriction that x should be less than 100. So you can't have 100 in the set. And now what happens is if you go beyond 10, 11 square, 12 square and so on, then the numbers that you would end up getting would definitely be greater than 100, and this would contradict the fact that x is less than 100. So this would not be satisfied, and hence those elements will not end up into the set. So what is the final set of numbers that we have? We have 0, 1, 4, then you have 9, 16, 25, 36, 49, 64 and 81. So that is so that is the set of 10 numbers that you have, and that is precisely your option B, which is what I think all of you have got. So okay, So I'll just ask you a question. So if I just modify this slightly, if I make this x greater than equal to 100, then what would be the cardinality of this set? What do you think?
Ma'am, in this set, the cardinality would be infinite because there is no limitation after x is greater than and equal to 100.
Okay, yeah, that is exactly that is a correct explanation. So what happens is, if you allow yourself to go beyond 100, then everything, all the squares after 100, which is 11 square, 10 square, 11 square, 12 square, and all the way up to infinity, they would all end up in the set, which is indeed an infinite set. Okay, good. So let's move on to the next question. So what you're asked to do is you want to show this identity about the operations on set. So what we will do is we will first begin by defining some basic operations on the set. So let's start by defining complement of a set. We will then define what do we mean by union, and we will define what is an intersection of sets. So these are basic operations that you can do on sets. So let's start by defining the complement. Okay, so let's say you have let's say these are all the sets of numbers that you can have. This is what is called universe of discourse, and let's say you have a set A which is contained in this. Now what does the complement look like? So complement is the this is denoted by A to the C, or I will also denote it by A bar. These are the same thing. So this is the set of all elements that are not in A. So if I try to draw this, so let's say this is an element which is in A, then it wouldn't belong to the A complement. And let's say this shaded area is the set of all elements that are outside A, and this is precisely what A bar would look like. So it's basically everything outside A, and this is, you can also denote this as U minus A. So is this okay? Yeah, okay, good. So now we will define what is a union of two sets. So let's say A and B are the two sets, and I want to define what the union is. So this is the set of all elements X, such that either X is in A or X is in B. So in terms of So in terms of the diagram, what this looks like is the shaded area, which is the set of elements that are either in A or in B or in both. This is what the union would look like. And now let's draw what the intersection looks like. So we define A intersection B. This is just a slight modification of the previous definition. So it is the set of all elements that are contained in both the sets A and B. So the keyword here is and. In the case of union, you want it to be or. It should be either in A or in B. Here you want it to be in both. So what does this look like? So yeah, anybody we would like to attempt what the intersection should look like in the diagram?
Ma'am?
Yes?
So when we shed the common area between A and B, then we can get the intersection of A and B.
Yeah, that is exactly the answer. So this shaded area here is what belongs to both A and B. So this is what the intersection would look like. So this is the area that is common to both. Okay, good. So yeah, I think with that in mind, now that the definitions are fresh in mind, maybe you could try to prove this identity. So this is on the LHS you have this set, on the RHS you have this expression. So yeah, so maybe you could try this for some time, and then we will discuss. Okay. Okay, so by U, what we mean here is U is the universe, which is the rectangle out here. Okay, so anybody, any ideas? How would you go about solving?
Then, to solve this question, we can first find the complement of set A and complement of set B. Then by intersection, then by solving its complement, we can get complement of set A as a universal set minus A set, and complement of B as universal set minus B set. And if the both sets are if the both sets have some elements as common, then the intersection of their complements would be universal set minus A set minus B set plus intersection of A plus B, A and B.
Okay, yeah, okay. That is on correct lines. Okay, so let me just write. I'm just writing complement as with the bar notation. I hope that is fine. So let me write down the equation we want to prove. So this is what you have. Okay, and yeah. So this is what you want to prove, and the idea is that I'll just write one approach, which is that to draw the diagrams for both of them and see whether they are matching. Okay, so these diagrams that we drew just now, these are what are called Venn diagrams. These are named after the person who came up with the representation. So let's try to understand how do we represent A complement intersection B complement in terms of diagram. Okay, so let's do this part by part. So essentially what we are doing is we are trying to represent the sets and not the numbers. So what you have on the top are numbers, and we're trying to show something like this in terms of sets. Okay, so at the moment, just let's just try to understand the approach. Okay, so also let me briefly define this notation A minus B. So this is a set operation that you perform on two sets. This is read as minus or set minus. So what does this look like in terms of Venn diagram? Say these are your two sets A and B, and what this means is all the elements that are there in A but not in B would belong to the set. So I'll call this S prime. So what does S prime look like? S prime is basically deleting the elements common to A and B from A. So this shaded area is what A minus B looks like. So in terms of set builder notation, this is the set of all elements X such that X is in A but X is not in B. Okay, so is this fine? Is the definition fine with everyone? So with that in mind, let's try to draw what the LHS and the RHS for this equation looks like. Okay, and once this is done, we can translate it to numbers. So that's one approach that can be done. So okay, maybe I'll explain this once. So why is it okay to solve this for sets? So let's say S is equal to S prime. So let's say these are two sets that are the same. Then what can you say about the cardinality of them?
Ma'am, are we talking about two same sets or a set and its complement?
No. So S and S prime are essentially the same sets. We are not talking about
Then their cardinality must be equal.
Exactly. So that's a fact. That's a fact that is not hard to see. So we will be using that. So the fact is, if you have two sets that are equal, then their cardinalities must be equal. Okay, so hence if you end up showing that, the idea is that if you end up showing that LHS is equal to the set on the RHS, then their cardinalities should be equal. So that is what we will end up doing. Hence it is sufficient to solve this in order to prove that. So that is the idea. So yeah, is this okay? Is everyone with me on the idea? Okay, so let's try to draw what A bar intersection B bar looks like. Okay, so A bar would be everything that is outside this area or outside this set A. And what does let's try to understand what B bar looks like. Yeah, so anybody, what would B bar look like?
Ma'am, B complement will look like the area shaded outside the area of B.
Yes, that is correct. So this is the shaded area is what B bar would look like. So now we have A bar and we have B bar. So what would A bar intersection B bar look like?
Ma'am, the elements that are common in A bar intersection B bar are universal set minus A set minus of A intersection B and universal set minus B minus B set minus A intersection B.
Okay, yeah, that is correct. So the shaded area here, that is exactly what A bar intersection B bar would look like. So this is the diagram that we have for the expression on the left, and we would like to show that you get the same expression, the same diagram for the expression on the right. So we will the idea is that you try to draw the diagram for the expression on the right step by step, just like what we did earlier. Now that we know what set minus looks like. Okay, so okay, so this is what this is the expression that you have on the right. And okay, so one problem here is that you can't directly so what we had on the top was numbers, and what you have here is set, so you can't use plus. So what you generally do is you use union, but problem is that it would not directly translate. So here you had plus, and you can't directly when you want to talk in terms of sets and not numbers, you can't directly use this plus. So the problem here is that you would have to write an appropriate set on the right hand side which would translate to the number that you wanted. So maybe what I'll do is that you can start looking at what the u minus a minus b, the union, the whole thing would look like. But yeah, so this is, for example, this is what u minus a would look like, and then you try to subtract b from it and so on. But okay, the point that I want to make here is that the problem with this approach is that the expression on the right hand side does not directly translate by simply replacing the pluses with union and so on. Okay, so yeah, so you would have to write an appropriate expression on this. So what I'll do is I'll get back to this, but we will look at a second approach for solving the problem. But in general, okay, so maybe I'll let you think about this. I hope this approach does not confuse people. So maybe stare at it. If there are any questions, then let me know. Okay, so I'll just summarize what we tried. So we wanted to write this thing in terms of Venn diagrams. We wanted to match it, but the problem is that you can't directly translate the expression to the expression on the right. So so what I'll do is I'll fix this in the notes. So I'll also add appropriate note to it. So when I upload the notes in the drive, I'll fix this. But what we will do for now is we will look at another approach for solving this. But in general, Venn diagram is also a valid method if you want to check whether two expressions for sets are equal. So I'll just call this approach 1 and I'll fix this in the notes. And the second yeah, so I hope the idea is clear, that instead of looking at cardinalities, you try to do it with sets and then lift it to the cardinalities. So what we will do now is we will look at a second approach for solving. Okay, so I'll get back to this later. So let me describe the second approach. So I'll just write this expression which we wanted to prove. So we want to show that the cardinality of A bar intersection B bar is same as cardinality of U minus cardinality of B minus cardinality of A plus the cardinality of A intersection B. Okay, so yeah, so for to do this, what we will do is we will use what are called De Morgan's laws. So let me just quickly write down what the De Morgan's laws are. So you have the complement of A union B is same as intersection of complements of A and B. So let's understand this with the Venn diagram. So I'll try to prove the first identity. So let's say this set is A, this is B, and Yeah, and what does A union B look like? A union B is the shaded area here. So what would the complement of A union B look like? So the expression on the left is A union B complement. So this would look like the shaded area outside. Okay. Okay. Yeah. And on the RHS you have A bar intersection B bar, and yeah, so A bar is precisely this area which is outside A, B bar is this area which is outside B, and when you do the intersection of that, then the area that is outside both the circles is what is common to them. So the newly shaded area in red, this is what A bar intersection B bar would look like, and both the equations match, both the diagrams match, and this is a simple way of verifying that the De Morgan's law is correct. So okay, yeah, Ojas, if yeah, sure, you can yeah, feel free to leave. I will be uploading this recording on YouTube, so you can check it from there. Okay, thank you for attending. Okay. So yeah, so this is one way of verifying that the De Morgan's law is correct, and similarly you can try and see the same. You can try to verify the same for the second identity as well. So now that you know both the laws, try to use this to solve to show the expression that we wanted to show. So this is A bar intersection B bar. So what identity would you use? Can you use some De Morgan's law to write this in a different way? Okay, so this is nothing but A union B whole complement, which is the first identity that we had. So is this okay with everyone? This is nothing but De Morgan's law. Okay, I'll admit this person. So now you can write this A union B whole complement as U minus union of A and B. Why is this? This is simply because of the definition of complement. So A complement is nothing but U minus A. So this second equality follows from the definition of set minus. So is this fine? Is the second equality fine with everyone? Okay, so yeah, so what we did so far is we simply used De Morgan's law, and then we used the definition of set minus. So if this is fine, then indicate the same, or if there are questions, then let me know. Okay. So okay, I'll just say a couple of more words. So this is what A union B would look like, and yeah, so the shaded area here is what A union B would look like, and what you have so far is yeah. So I'll just maybe write this again. So what you have so far is U minus So a bar intersection b bar is nothing, is that because these two sets are equal, you have that the cardinality of this is same as the cardinality of u minus a union b. And now since these two sets are disjoint, you can write this as cardinality of u minus cardinality of a union b. Okay. So yeah. So yeah, so this shaded area outside A and B is precisely what we have calculated so far. And now we want to simplify this further. So does anybody have any doubt at this point? Okay. So now what we will do is so let me just write down the expression that we had. So this was u cardinality of u minus cardinality of A union B. And now the question is I want to expand A union B. So let's try to do this with an example. Let's say that the number of elements in set A is 5, the total number of elements in set B is 7, and you have two elements that are common to A and B. So the question is, what is the size of A union B? So this is just a toy example to help us derive an equation for A union B. So what would this size be? Okay. Okay, so please note that 5 is the total number of elements in A and 7 is the total number of elements in B and 2 is the number of elements that are common. So yeah, so now given that, what do you think would be the size of this A intersection, A union B? So yeah, is this making sense? Okay, so what I'll do is, my claim is that the answer is 10, which does not match with any of the answers in the chart. So what we'll do is we'll justify this with even simpler example. So let's say I have a set which consists of apple and banana, and then I have another set B which consists of three fruits. It has banana, then say it has pineapple, and it has mango. Okay, so what is the cardinality of set A here? It is 2 because it has two elements, apple and banana. And what is the cardinality of B? So B consists of banana, pineapple and mango. So what is the cardinality of B? It is 3 in this case. Okay. So what is the cardinality of A intersection B? It has one element, banana. So the cardinality is 1. Now looking at this example, what can you comment about the size of A union B? Okay, so let's try to write down this set. What does A union B look like? Okay, so I see some answer. The answer is 4, which is correct. So A union B is apple, banana, pineapple, and mango, and there are precisely four elements here. So the answer is 4. So keeping that in mind, notice that we did not count banana. We ended up counting banana twice in A and B, so we had to subtract it once. So similarly, we will apply the same logic here. 2 is that the two elements that are common to A and B are getting counted twice. That is, so we would have to subtract it. So let's write this very clearly. So the set A consists of apple and banana. The set B consists of pineapple, banana, and mango. And therefore the size of A union B is size of A plus size of B. So if we just blindly add it up, what happens is, if we blindly add them, then the bananas are getting counted twice, once in the set A and once in the set B. So to account for that, what we will do is we will subtract the overcounting by a factor of 1. So what we will do is we will subtract A intersection B from the resultant set. So this is the expression that you get, and in this case the number of apples, the size of A is 2, the size of B is 3, and the size of the intersection is 1. So if you plug it into the formula, you get 2 plus 3 minus 1, which is 4, which matches with the answer that you had given. So going back to the example that we had here, if you plug this into the formula, you have 5 plus 7, which is size of A plus size of B minus size of intersection. So this would be 5 plus 7 minus 2, and that would turn out to be 10. So the minus 2 is to justify for the fact that you're counting A intersection B twice, and hence you have to subtract it once. So that's why you would end up getting your answer as 10. So is this making sense with everyone? So what I'll do is I'll just replace this A union B formula that we just wrote below into this equation. So I'll call this identity star, and this follows from the identity star. So if you just multiply and open the brackets, then you get size of U minus size of A minus cardinality B plus cardinality of A intersection B. So this is precisely what we wanted to prove. So is this making sense, or if there are any questions about this, then please let me know. Okay, so if this is fine, then we will move on to the next question. So this is also similar to what you did just now. Here you just basically want to apply the identities that you learned, and also read the C as complement. So you simply apply the De Morgan's laws and show that the two expressions are equal. I'll just write down the laws here so that you can refer to it.
करेगा हाथ में अक्षर पुष्प प्रदर्शना और सारी
Okay, so let me write down this expression on the LHS. This is this is the complement of A union B intersection C is complement. So I can simply, okay, maybe I'll write this as D. So B intersection D is B intersection C is D for me. So I can equivalently write this as A union D complements whole complement. So D is simply written as B intersection E. Okay. So now what we will do is we will apply the De Morgan's law. So this gives that this is equal to A bar intersection D complements complement. So this simply follows from De Morgan's law. Okay, so what we have done is we have simply written B intersection C as D. We replaced it in the formula and then we applied De Morgan's law. So this is what we have at right now. Now the question is what would D complement look like? So yeah, if there are any questions about the two steps that we wrote, then let me know. Or otherwise please think about what would D complement look like. Okay. So my claim is that I can simply write this as A bar intersection D. Why is that? Because notice that the complement of a set would be the same set. So you can see this with the diagram visually. So say this is your universe, this is the set A, and the shaded area outside is A bar. Now the complement of A bar would be everything that is outside A, and that's nothing but everything that is in A. So this is a simple property of complements, that complement of the set is nothing but the same set, and using the property you get that this is same as A bar intersection D, and D is nothing but B intersection C. This is how we had defined D. So I'll just simply replace it with A bar intersection B intersection C, and this is exactly what you wanted to prove on the RHS. So what we did is we simply applied the De Morgan's law, then we used the property of complements, and we in two steps we got the expression on the RHS. Okay, so is this fine? Okay. Good. So the third question is similar, and this is also quite simple. So you can try to solve this. So I'll just write the question. You have that A is a subset of B. So this is the notation for a subset as such, and B is a subset of C. And what you want to find out is what is the cardinality of the set A union B union C. So maybe think about it for a couple of minutes and then let me know what you think. Okay, good. So I think most of you have got it right. So let's see why this is. So you have that A is a subset of B. So A would be completely contained inside the set B. And furthermore, you know that B is a subset of C. So C would completely contain the set B. So it may or may not have more elements, but B is definitely contained inside C. So what would be the union of A union B union C? That is nothing but the set C, and hence the cardinality of the A union B union C is nothing but is the same as the cardinality of set C. This was from the property, from the fact that we stated earlier in one of the questions. So yeah, the shaded area here is basically what the cardinality of C would look like. So C is the correct answer, which is also what all of you answered. Okay, good. So now we will look at the next question. So let's say you have a class of 110 students, and say M is the set of students that are interested in that take mathematics, and say S is the set of students that take statistics. And so from the data that is given, you know that there are exactly X many students who take both math and statistics, and there are 2x plus 20 many students who take mathematics. Then there are 2x plus 30 many students who take statistics. Okay, so what I mean by 2x plus 20 is that it is the whole area and not just the area that is outside the intersection. Okay, so the what you know additionally is that there are no students who take neither maths nor mathematics. So the area outside is completely empty, and what you are asked to find out is what is the value of X. So I'll let you think about it for a couple of minutes and we will discuss. Okay. Mm-hmm. Okay, so let's write down the values that we have. So M is the set of students who take mathematics, and we know that size of M is 2x plus 20. Then the number of students taking statistics is 2x plus 30, and the number of students who take both maths and statistics is X. Now the question that we have is what is the cardinality of M union S. So before that, maybe let's understand what is the cardinality of the universe. Okay, so notice that there are 110 students in the class, and this is the set of all the students, which is 110. So the size of universe is 110. Okay. Okay, so now the question is, what is the cardinality of M union S's complement? So notice that we have mentioned in the question that there are no students who take neither mathematics nor statistics. So the area which is outside the union of the set would be empty. So what would be the cardinality of this set? So this is simply 0 because there are no elements in the set. Okay, so good. So the cardinality of this would be 0. Okay. So, so basically, this shaded area here is what M union S's complement would look like, and this is that there are no elements in it, so the cardinality is 0. So now, given this, we will simply apply the identity that we had written earlier. So this identity star that we had defined earlier, we will write this again, and we will plug and place the values and calculate the value of x. So this is nothing but okay. So M union S is nothing but M bar union S bar. This is what you have from the De Morgan's law. So maybe I'll write this over again. So you have M union S whole complement is same as size of U minus size of M union S. This follows from the definition of complements, and further yeah, so this is basically everything outside M union S. So this is same as size of U minus size of M union S. And further, what we'll do is we will expand on the second term here, which is M union S. So from the identity that we wrote earlier, we know that the size of A union B is same as size of A plus size of B minus size of A intersection B. So we will simply use this formula, and what this gives you is size of M plus size of S minus size of M intersection S. And if you open the brackets, then what you get is cardinality of U minus cardinality M minus cardinality S plus cardinality of M intersection S. Now what we will do is we will simply plug okay, is this okay? Okay. So now what we will do is we will simply plug and place the values that we had written earlier into the formulas that we have. So what is the cardinality of U here? You have 100 minus cardinality of M minus which is so the cardinality of the set on the LHS is 0, so you get that the size of M union S is 100. Okay, so thank you for pointing out, it is actually 110. So okay, I'll just write it again. So you have that cardinality of M union S is 110. Now we will plug and place the values for the equation, for the second equation that you have. So size of U is 100, then size of M is 2x plus 20, then size of S is 2x plus 30, and size of M intersection S is x. So now you have an equation which is in terms of x, and you simply want to solve for x. So is this okay? let me know if there are any questions, or if this is fine, then indicate the same. So what we did here is we simply looked at this equation, plugged in the values, and we ended up getting the equation at the bottom. Okay. So I'll just write the equation that we had written earlier. You have 0 is equal to 110 minus 2x plus 20 minus 2x plus 30 plus x. And now you simply want to solve for x. That gives you 3x is equal to 110 minus 20 minus 30, which is 60, and that basically gives you x is equal to 20. So is this clear? Okay. So yeah, what we basically did is we simply used our identity, plugged in the values, and solved for x. Okay. So if this is clear, then we will move on to the next question, which is also based on a similar idea. So let me define the problem for you. So what you have here is you have the set of all car owners, which is 500, and then you have a set of people who own Audi, so there are 400 of them, so size of A is 400, and you have a set of people B who own BMW, and say there are 200 people who own BMW, and additionally you know that the number of people who own both Audi as well as BMW is 50. So this is what it looks like in the diagram. You have 50 people in the intersection, you have 200 people in total in the set B, and you have 400 people in total in the set A. And the question is the data consistent, or is there something wrong with the okay, so okay, good. So I think you have got the correct idea. So let's understand the solution. So what you know is that the total number of people that are there in the universe is 500, and we will apply this formula that we saw earlier. You know that the cardinality of set A union B is cardinality of A plus cardinality B minus cardinality of intersection. So just plugging in the values, what you get is that the number of people who own either Audi or BMW is 550. Okay, but the problem with this is that so let me write this. So the number of people who own either Audi or BMW is 550, and but the total number of people that you have, the total number of car owners is, that means the total number of car owners should at least be 550. So why am I writing at least is because the data that we have written only accounts for the number of people who have Audi or BMW, but there could be people who own other kinds of cars. So this number can only shoot up. It can't ever get lesser than 550. But the data also says that you only have 500 car owners, so there are only total number of there are only 500 car owners in total. But if you look at the data that you have, then number of people who own Audi or BMW itself is 550. So this is a clear contradiction, and yeah, that's the inconsistency in the question. So yeah, so now we will move on to the final question. So this is a bit it's based on similar ideas that you saw earlier, but it might get a bit tricky. So I'll let you think about it. I'll just describe the problem. So the problem is that there are three types of people in the students in the school. You have classified them as geeks, the wannabes, and the athletes. And this is the set of all the students that you have. Okay. Now what you know is that there are totally 1,000 students in the school, and you have this data for how many students are geeks, how many are wannabes, and you know the data for all the intersection. Okay, so it's possible that a student is a geek and a wannabe, or it's possible to have all kinds of combinations, but it cannot be that given a student you can't classify them as neither a geek nor a wannabe nor an athlete. So that is an additional constraint that you have. So these are the values that you have for all the intersections, and the question we are asking is, what is the total number of students who fit in all the three intersections? That is, what is the cardinality of G intersection W intersection A, which is the shaded area here. So this is something that we want to find out, and yeah, so you can do this using the ideas we saw earlier. So what I'll do is I'll maybe wait for a couple of minutes, and if you have any questions about the problem, or if you have any ideas, then let me know. Okay, so let us write down the values that are there. Okay, so Okay, so yeah, let's try to see if there are any answers. Okay. Okay. Okay, so let's start by writing down these values. So G intersection W intersection A, this is what we wanted to find out. And so this is the set of people who are geeks as well as wannabes as well as athletes. And yeah, so what I want is I want to write an expression. I want to write this as a sum of cardinalities of some other set. So what would
Ma'am, may I?
yeah, sure, please.
This cardinality of G intersection W intersection A equal to cardinality of G plus cardinality of W plus cardinality of A minus cardinality of G union W union A.
Oh, okay.
Then I substitute all these values, ma'am.
Okay, so the expression that I have is different from this, but we will get back to this. We will look at the expression that I have in mind. We will solve it, and then we will see whether the answer matches with this. But also, if others have something different from this expression, then I'll note it down, and then we can look at it together. So yeah, let me write down. I'll mark this as the expression that was suggested by Rinda, and yeah. So the expression that I have in mind. So I'll write it down here. So this is then you subtract all the possible intersections that you have, and so all possible intersections of size 2, and then you add the union of G, W and A. So this is the expression that I have in mind, and what we will so let's see how to derive this. Okay, so I'm going to compare this with the idea that this expression that we derived earlier. So we said that the cardinality of A intersection B is same as cardinality of A plus cardinality of B minus the cardinality of intersection. So we will try to derive it the same way that we did earlier. Okay, so let's see how to do that. Okay. Okay, so let's say the shaded area here is the wannabes, and the shaded area in black, this is what the athletes is. And the point that I'm trying to make here is that if you simply add and subtract the union, then you may not have counted everything exactly once. So let's see what I mean by that. So suppose this is the set of people who are geeks and nothing else. B is the set of people who are only wannabes and nothing else, and C is the set of people who are athletes and nothing else. Then E is the intersection of the geeks and wannabes. F is what the intersection of geeks and athletes, and G is the intersection of everything. So what we want to find out is the value of G, which is the intersection of everything. Now let's see what happens if I'll just bring the expression that was suggested in the by one of you, and I'll see whether we are actually counting G. Okay, so when I say A, what am I counting in from this set? I'm counting A, then I'm counting G, I'm counting F, and I'm counting E. So is this okay? When I say that I'm counting A, what I'm exactly counting is the elements in A, F, G as well as E. Okay, so this is precisely the set A that you have. So now when when I'm counting B, what are the elements that get counted? Okay, so you are basically counting B, E, G and D. So this is what gets added when you count B. And what happens for C? Okay, so what you count is F, G, D, C. I hope that is what you meant in the chat. So what the elements that you are counting is F, G, D and C for the set C. Is this okay? Okay. So now let's write what gets counted when you do A union B union C. What are the elements that get counted? Okay, so this is basically A plus B plus C and all the way up to G. So you are counting everything exactly once. That's what the union is, and I'm writing minus here because we are subtracting the A union B union C from the set. So now let's see what gets counted. So we are adding some things, we are subtracting some things. So what is getting counted in effect is, so A's get cancelled, B get cancelled, E gets cancelled, C gets cancelled, D gets cancelled, and F gets cancelled, and G gets cancelled. So what has survived is you have G plus F plus E plus D. So what happens is you over counted the intersection twice, and you over counted DFE once. So this is what is happening when you write this expression. But what I actually wanted to count was just G. So if so what we did is we just saw what got counted in this expression, and it does not match with what I wanted to count. So so this is an extra factor of G plus D plus F plus E that is getting over counted, and I want to subtract that. So I will modify the expression appropriately so that I end up counting exactly G and nothing more. Okay, so let's see how to do that. If there are any questions, then let me know. Is this making sense? Okay, so let's see how do we write the union so that we are exactly counting G. So I am writing the expression that I had written earlier in the previous slide. So this is sum of the individual set minus the intersections of two sets one at a time, and then adding the cardinality of the intersection of three sets. Okay, so let's draw the same figure again. I'll use the same notation. So this is ABC, then you have D, E, F and G. So what you have here is a plus b plus c plus d. This is the expression on the LHS that you want to count. So this is exactly what I want to count, and this should be same as what you're counting on the RHS. So let us see what gets counted on the RHS. So like we said earlier, so if you add a, b and c, then you are counting a plus e plus f plus g. For b you are counting b, e, f, d, and for C you are counting C, D, F, G. So is this making sense? Okay, I think the set for B, the values for B should be different. So please tally it with your answers, and if there's any difference, then let me know at this point. Okay, so C plus D plus F plus G. This is what is there in the set C. Okay. So this is what you have when you added a plus b plus c. Now what we're doing is, notice that in this set, E got counted twice, once for A and once for B. A, B and C, this got counted exactly once. This is what we wanted. But notice that E got counted twice, F got counted thrice, and D got counted twice, and G also got counted twice. So there is some over counting that is happening at this stage when we only added A, B and C. So what we want to do is we want to subtract appropriately so that this over countings get cancelled off in some sense. So is this making sense? So what we did is we just wrote what is getting counted, and now we want to modify the rest of the counting. So if there are any questions about this, then let me know. Okay. So yeah, so E, D and G is the intersection part which got counted twice, and F is the intersection of everything which got counted thrice. So I'll just pull this figure on the next page so that we can do the rest. Okay, so now what are the elements that we are subtracting? We are subtracting A intersection B. We are subtracting, so what are the elements in A intersection B? So this is nothing but E plus F. Yeah, exactly. So what you get is E plus F. What are the elements for B intersection C? This is F plus D. And what are the elements for A intersection C? This is G plus F. Okay, so these are the terms that we are subtracting from the sum that we had obtained so far. So what would happen is this E and the E in the previous one gets cancelled off. F gets cancelled off. Another copy of F gets cancelled off. Then one occurrence of D is cancelled off. Another copy of F is cancelled off, and G gets nicely cancelled off. So what you are left with, okay. So what we essentially did is we added the individual sets, then we subtracted the intersections. So and now what we are left with is simply A, B, C, E, G and D. These are the terms that have survived. So we will write this freshly. So what is survived is A, B, C, D, G, E. And what is missing from this set is what is F. And the only term that is missing from the expression on the LHS is F. So what I'll do is, to account for it, I'll simply add A intersection B intersection C, which is nothing but F, to the set, so that I match the two expressions. Okay. So what we get is A union B union C is the sum of cardinalities of the individual sets, minus the cardinalities of two intersections and adding the cardinality of the intersection of three sets. So this missing term here is F, which is A intersection B intersection C. So yeah, so now this gives you exactly the term on the LHS. So this is exactly what we if you look at it, this is exactly what we did in the previous formula. So this is what we had written earlier. So A union B is, if you simply add A and B, then you get A plus C. If you add B plus B, then you get B plus C. And therefore, since you're overcounting the intersection once, you have to subtract it twice. So here in the case of 3, what's happening is that this intersection of two sets is getting counted twice. So we are subtracting it once, and the intersection of 3 elements got counted thrice in the single elements and got subtracted thrice in the two intersections. So it got nullified in effect, and therefore we are adding it once. So is that making sense? So this is this idea of writing the cardinality of union of two sets. This is called the principle of inclusion exclusion, and it's rightly called so because what we do is that at each step we keep on adding one at a time, and we decide which elements are to be included, which elements are to be excluded, so that the count matches exactly. So this is the key takeaway for the problem. And please let me know if there are any questions. Okay, so now I'll just copy this problem on a fresh page, and we can substitute the values in the formula and see if that matches with any of your answers. Okay, so this is the question. So let's and what I want to find out is the value of G intersection. I'll just write the formula that we wrote earlier by principle of inclusion exclusion. So what is the total number of students that are there? Okay, so let's maybe start with simple example. So what is the cardinality of G? What is the total number of geeks? Okay. So the number of geeks that you have is 310. The wannabes, the number of wannabes is 650. The number of athletes what is the value of G intersection W?
170.
Right. So W intersection A?
180.
Okay. And A intersection G?
150.
Okay. And finally, what is G union W union?
1000.
Okay, good. So this is what you have, and now we will simply use the principle of inclusion exclusion formula, and we will plug and place the values. So let's see what that turns out to be. So cardinality of G union W union A is the sum of cardinalities of G W A minus the cardinalities of pairwise intersections, and finally you add the intersection of all the three sets. So what we will do is we'll simply substitute the values that you have. So 1000 is equal to 310 plus 650 plus 440 minus 170 minus 180 minus 150 plus G intersection W intersection A. This is exactly what we wanted to find out anyway. So I'll just call this X for now, and we will solve this for X. So you can also parallelly do this computation, and yeah, if you come up with an answer, then let me know. Okay. So what you're left with is 1000 minus 150 minus 310 minus 440 is equal to X. And if you sum this up, this turns out to be 900, and that gives you that X is equal to 100. So okay, I think this is also what you guys have written in the chat. So yeah, so the number of athletes and geeks and wannabes in the school is 100, and the key idea that we use here is what is this principle of inclusion exclusion, where we added and subtracted the sets appropriately. So I could also go one step further. So suppose I give you 4 sets now instead of 3. I give you 4 sets and I ask you what is the cardinality of A union B union C union D. Then what would be your what would be your approach? Okay, so maybe I'll just describe the idea. I'll just write down the expression. So you add all the cardinalities of all the sets, then you subtract the intersections, the pairwise intersections of the sets, which is minus A intersection B minus A intersection C minus B intersection D. So there are four sets here, and you are choosing 2 at a time in the pair. So the total number of elements here would be 4 into 3 by 2, which is 6. So you end up getting six pairs here. So I'll write the remaining ones. You have A intersection D minus B intersection D. So this is accounting for the 2 intersections. Now what happened is that earlier you had overcounted some elements, so you subtracted some of them, then you ended up undercounting them, so we will have to add some of them. So what we'll do is we'll add the 3 intersections of them. So this is what you get, and then finally, because you ended up overcounting again, you will subtract A intersection B intersection C intersection D from the set. So I think the answer that is there in the chat is almost close to what we are trying to describe here, but it's slightly different from what is there. So okay, so this is also what follows from the principle of inclusion exclusion, and you can follow the same steps that we did earlier, and you can try to prove this in general. So yeah, right now I'll not say more about this, but I'll let you think about this offline, and if you have any questions about it, then we will take it up in the next session. So but I hope that I hope that you're convinced about the idea that if you want to show something like an expression like this for any finitely many sets, then you would end up doing something like adding and subtracting elements and overcounting, undercounting again and again to finally match with the solution that you wanted. So if there are any questions about this, then let me know in the next session. So next we will meet on next Friday 6 p.m. to 8 p.m. And what we will do is we'll start with the logic part, which is the content for the next week. And since your problem set or assignment deadline is due due this week, what we will do is we'll look at some of the solutions for this assignment 1 question. So if you want me to specifically look at some questions that you would like to be addressed, then you could either comment on this video, which will be uploaded on YouTube, or you could use the discussion forum on the Swayam portal. So either is fine. So I'll look into it, and I'll try to, I would prefer to take those questions. So yeah, so next session would be a combination of concepts on logic and some of the questions on problem set and assignment 1. So if there are any questions about what we discussed today, then I'll wait for some time. Otherwise, feel free to leave. I hope this session was helpful, and I'll see you next week. Okay, so others, are there any questions?